Hey, welcome. Let's talk about the unsung hero of our entire modern world, reinforced concrete. Yeah, I know, it sounds boring. It's that gray stuff that's everywhere, our buildings, bridges, you name it. But hiding inside that simple exterior is a set of brilliant, honestly, kind of mind-bending rules that literally keep our world from falling down. So let's get right into it.
But here's the thing. To understand why concrete is so ingenious, we first have to talk about its secret weakness. Because this stuff, for all its strength, has a really big, fatal flaw.
So, what is it? I mean, this is the material we use more than anything else on the planet besides water. We trust our lives to it every single day. So what's its hidden vulnerability? Well, it's a total paradox.
You see, concrete is an absolute beast when you squeeze it. That's called compression. But the moment you try to pull it apart or stretch it, what we call tension, it's shockingly weak. It just snaps. Steel, on the other hand, well, its real superpower is its incredible strength when you pull on it. So you've got these two materials, and each one is basically the superhero the other one needs. And this is where the genius starts. Reinforced concrete is just that perfect team-up. We take steel bars, we call them rebar, and we embed them right inside the concrete. So now the concrete does what it does best. It handles all the squeezing, and the steel inside takes care of all the stretching. It's a perfect partnership. Okay, so now we have our super material, but just having it isn't enough. Engineers have to use it in a really specific, almost counterintuitive way. The goal isn't just to make things strong, it's to make them fail safely. Yeah, you heard me right. The plan is to design for a safe failure. The entire philosophy behind designing with this stuff is that failure should never be a surprise, ever. If a building or a bridge is going to have a problem, it has to scream for help first. It needs to give us really obvious, visible warnings long before it actually collapses, so people have time to get out. So how can that go wrong? Well, your first instinct might be, hey, let's just cram a ton of extra steel in there to make it stronger, right? Turns out, that's the most dangerous thing you could possibly do. In what's called an over-reinforced beam, there's so much strong steel that the weaker concrete is forced to fail first. And concrete fails by shattering. It's sudden, it's explosive, and there's absolutely no warning. It's so dangerous, it is completely forbidden by every building code on the planet. Then you've got the theoretical perfect world, the balanced design. This is that sweet spot on paper where the steel and the concrete are so perfectly matched, they fail at the exact same instant. It's super efficient, sure, but in the real world, it's just too risky. It's like trying to balance a needle on its point. The slightest mistake could tip it over into that sudden, dangerous failure we just talked about. Which brings us to the safe, clever, and preferred way to do it, something called an under-reinforced design. You're not going to believe this. Engineers deliberately limit the amount of steel they put in. Why? Because this forces the steel to be the weak link. And steel doesn't just snap. It's ductile. It stretches and yields first. That stretching makes the whole beam visibly sag and crack, giving everyone a clear, impossible-to-miss warning sign that something is seriously wrong. That's the safe failure that saves lives. Okay, so that's how we handle bedding in things like floors and beams. Now, let's follow the load down the building. Let's see how these same ideas apply to the columns and foundations that have to carry all that weight down into the earth. Reinforcing a column is basically a three-step dance. First, you place the main vertical steel bars that are going to carry the bulk of the load. But second, and this is absolutely critical, you add smaller steel ties that wrap around those main bars. Think of them like the hoops on a barrel. Their only job is to stop the main bars from bursting outwards under all that pressure. Then, you pour the concrete around that whole steel cage. Without those ties, the column would just explode. So once all that load gets down to the foundation, we face a totally new enemy. It's called punching shear. The best way to picture this is to imagine pushing a sharp pencil through a piece of cardboard. That is exactly what a heavily loaded column wants to do to the concrete foundation it's sitting on. It's a huge risk that engineers have to very, very carefully design against. And finally, there's one more super simple but ridiculously important detail: concrete cover. This is just that outer layer of concrete that protects the steel rebar from the outside world. You can think of it as the structure's armor. It's what shields the steel bones from moisture, which causes rust, and from fire and chemicals. If you don't have enough cover, the whole system just rots from the inside out. All right, let's switch gears. We've talked about buildings, but what happens when you're not just fighting gravity, but you're trying to hold back the immense, constant forces of nature, like earth and water?
So take a retaining wall, the kind that holds back a hillside. It's fighting a two-front war. First, the pressure from all that earth is constantly trying to tip the whole thing over. We call that overturning. At the same time, that pressure is trying to just shove the entire wall forward on its base. That's called sliding.
And the solution here is just so elegant. Engineers actually use the wall's own massive weight as a weapon. They use this principle called the middle third rule to design the walls so that the combined force, from the soil pushing and the wall's own weight pushing down, is aimed directly into the middle part of its foundation. This keeps it from tipping and makes sure the pressure on the ground beneath it is nice and even. It's a perfect balancing act. Now, let's flip that whole problem on its head. What if the force isn't pushing in, but pushing out, like inside a giant concrete water tank? Sure, it has to be strong, but now the number one absolute top priority is making sure it is completely 100% leak-proof. And when I say leak-proof, I really mean it. A tiny crack in a normal beam might be okay, but in a water tank, the maximum allowable crack width is just 0.1 millimeters. To give you some perspective, that's about the thickness of a single human hair. The precision needed is just incredible, all to make sure not one drop gets out. Okay, so all of these rules have made concrete incredibly safe and reliable. But what if you could change the rules of the game altogether? Well, let's look at an advanced form of concrete that does exactly that.
This stuff is called pre-stressed concrete, and the concept behind it is pure genius. Before that piece of concrete is ever asked to hold up a single car or train, engineers thread these high-strength steel cables through it, and then use powerful jacks to stretch them incredibly tight. This action permanently squeezes the concrete, putting it into a state of pre-compression.
So why is this such a game changer? Because that built-in squeezing force is always there, actively fighting against the stretching force that loads will create later on. What you get is a structure that is virtually crack-free. This lets engineers design things that are way thinner, much lighter, and can span much, much longer distances. It's what makes modern highway overpasses, massive bridges, and huge stadium roofs possible. So we have all these fundamental rules, these invisible principles that have built our modern world and made it incredibly safe. But it all leads to one final, huge question. In our world of tight budgets, impossible deadlines, and really bold architectural dreams, how do engineers balance these non-negotiable laws of safety with the constant pressure to build cheaper, faster, and bigger? That's the real challenge, and it's at the heart of engineering today.